Hello everyone, I am Dr. Ritish Kumar, going to give the lecture over the subject for the subject of communication engineering, and the topic is frequency modulation. So here we will discuss about what is the modulation and what is the utilization of frequency modulation, and then we'll discuss about the characteristics of the frequency modulation such as narrowband frequency modulation and wideband frequency modulation. First, we will start from the general equation of frequency modulation as well. Now, now the as you all as what is the modulation? Modulation is nothing but uh, 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 that converts the low frequency signal to the high frequency signal. In other words, we can say modulation modulates the properties of carrier signal in accordance with the value of instantaneous value of the message signal. Either it can be a amplitude, phase and frequency. So here we will talk about the frequency only. So this is the university syllabus. So the syllabus is the syllabus has the five units. Here we will the frequency modulation lies in the second unit as well. So this is and first unit is totally based on the amplitude modulation, then the angle modulation. Second unit and third unit is based on the random variable and random process, and fourth unit is the pulse modulation, and the fifth unit is totally based on the digital modulation technique such as amplitude shift keying, frequency shift keying and phase shift keying as well. So these are the recommended books. The first I will mainly focus on the first book is a Simon Haken communication system, published by the John Wiley and Sons, and second book is the Torrent Schilling principle of communication system. These two books are very well known books and very good books to rectify your problems and issues. By reading these books you can solve all the problems as well. So start with the introduction. So here we will talk about the frequency modulation. So here I have categorized the modulation techniques. For analog communication system, we have baseband modulation scheme and the passband modulation scheme. So in the baseband modulation scheme, we have two kind of modulation. The first one is the amplitude modulation and second one is the angle modulation. So amplitude modulation, what is the amplitude modulation? So first of all, modulation is the technique by which you can convert a low frequency signal into the high frequency signal. So apart from this, if we talk about the amplitude modulation, it specifies that the amplitude of the carrier signal changes in accordance with the instantaneous value of the message signal. If we talk about the amplitude, so in the amplitude modulation, we have different kind of modulation techniques. The first one is the DSV, that is the double sideband quadrature amplitude modulation, single sideband, that is SSB, and vestigial sideband modulation, VSB, SC. So these are the different kind of amplitude modulation. So in this case, if we talk about the in terms of efficiency modulation, so VSV-SC is the more efficient system related to the DSB-SC and SSB-SC. Now the angle modulation. So in terms of angle, we suppose if I write the equations like for the carrier signal, suppose if I write the carrier signal CT is equal to, in terms of analog signal, AC cos 2 pi FCT, right? So this is the phase of the carrier signal, and this is the carrier signal frequency, and this one is the amplitude. So so in the angle modulation, we can say there are two possibilities to change the frequency, either directly or indirectly. If you change directly, if you change the frequency directly, then it will known the frequency modulation. If you change the phase directly, then it will known as phase modulation. In that means if the angle of the carrier signal changes in accordance with the instantaneous value of message signal, then will known as, then this phenomena is known as angle modulation. So so if I write the phase is theta I, so theta, this is the phase, so you can change the phase by changing the phase of frequency as well. So you have two modulation in the angle modulation. The first one is the phase modulation and second one is the frequency modulation as well. So if I talk about the passband modulation scheme, there are some kind of passband modulation schemes such as frequency modulation, frequency division multiplexing, time division multiplexing, code division multiplexing. So FDM, TDM or CDM as well. So here we will focus over the frequency modulation, which lies in the angle modulation as well. So frequency modulation, as I already told about the what is the frequency modulation. If you change the frequency of carrier signal in accordance with the message signal, in accordance with the instantaneous value of the message signal, then this phenomena is known as frequency modulation. So here you can see angle modulation, and angle modulation encompasses phase modulation and frequency modulation. The phase angle of a sinusoidal carrier signal is varied in accordance to the modulating signal. Modulating signal is nothing but the message signal. You can say message signal or baseband signal as well. Right. So initially here I will write the carrier signal by A cos theta CT, right? Here theta C is the angle before the modulation, and A cos theta IT, here theta IT after the modulation. Right. So now come to the point, the general equation. What should be the general equation of frequency modulation? So here you can see here the frequency of the carrier signal. Here FIT is representing the frequency after the modulation, FC before the modulation carrier frequency, and this is the message signal or baseband signal. Here MT is the baseband signal or message signal, or you can see the modulating signal as well. So here you can see the carrier frequency is varied in accordance with the instantaneous value of the message signal here. So here you can see FIT is equal to FC plus KF MT. This is the variation in the frequency after the modulation, which is depend on the modulating signal, that is nothing but the message signal, where KF is the frequency sensitivity of the modulator expressed in the hertz per volt. Right. So if you integrate this, if you integrate the above equation and multiply by 2 pi, then you will get the angle, that is theta 80 is equal to 2 pi FCT plus 2 pi KF 0 to T MT dt. This is nothing but you are integrating this equation like from 0 to T. So you will have the first term is, if you integrate this like FC plus KF MT dt over the 0 to t. So you will have fct plus kf 0 to t mt dt, right? Now you will have to multiply with 2 pi, then you will get 2 pi fct plus 2 pi kf 0 to t mt dc. So it comes like in this way. So you will have, at last you will get theta it, that is the angle after the modulation will be 2 pi fct plus 2 pi kf 0 to t mt dt. So you are integrating this equation from 0 to t here. Now the frequency, so you can represent the equation of frequency modulation here. Initially I already told this is AC cos theta it, right? So you can replace this theta it with this equation. So you will get the equation st is equal to AC cos 2 pi fct plus 2 pi kf 0 to t mt dt, right? So this is the general equation of frequency modulation. You can see here, this is general equation of FM, right? So message here, mt is an arbitrary message signal. You can consider a single tone message signal or multi-tone message signal as your requirement. So I hope this one is clear to all of you. Now the relationship between PM and FM. PM is phase modulation and frequency modulation. So you can see that in the general equation there is a integration part 0 to t. So this is the phase of the carrier signal. If you directly if you first, so you can see if you pass the message signal through an integrator and apply this to the frequency apply to the phase modulation, then you will get the frequency modulation. So you can see here, first you have to pass the modulating wave, that is the message signal, through the integrator, then you will get this one 0 to t mt dt. Then if you then you have to pass this signal from a phase modulator, then you will get the frequency modulated wave here, right? In reverse way, if you first pass the message signal through a differentiator, then apply to the frequency modulation, then you will get the phase modulated wave. So this is the relationship between the phase modulation and frequency modulation. So for the phase modulation, first you have to pass the signals from the integrator, and for the phase modulation, first you have to pass the signal from the differentiator. Then you will get the relationship between phase modulation and frequency modulation as well. These are the waveforms that you can see here. This is the here A, B, C, D, E. Total 5 waves are here, and the representation of these 5 waves are respectively with A is equal to carrier wave, B is the sinusoidal modulating signal, C is the AM signal, D is the PM signal, and E is the frequency modulated signal. So this is the A is the carrier signal, A is the carrier signal, right? So this is a high frequency signal you can see here, right? And this is a message signal, or you can say baseband signal, or modulated signal. This is a low frequency signal as well, you can see here. So here you can observe here there is a variation in the amplitude of the carrier signal. That's why we are saying this is a amplitude modulated signal. Why? Because here the amplitude of the carrier signal is varied in accordance with the instantaneous value of the message signal. Here you can see there is a low value of the message signal, then you will get the low amplitude. Here you can see the value is high of the message signal, then you will get the maximum value of the amplitude here. So this is the variation in the amplitude. That's why we call this the amplitude modulation here. Now you can see here in the D diagram, here you can see the amplitude is constant, right? Amplitude is constant while the frequency is getting increase or decrease with respect to the instantaneous value of the message signal. Here you can see, first you will have the high frequency, low frequency, low frequency, and high frequency, right? So in the last you will see again the frequency variation in the carrier signal, while uh, the amplitude is constant in both last two frequency modulation and phase modulation. So you can observe here the high frequency you will get at the maximum value, right? And at low value of the message signal you will get the low value of the frequency. So this is again we can say here the frequency is varied in accordance with the message signal instantaneous value here, while keeping the amplitude or amplitude constant, right? So you can see there is a little variation in between frequency modulation and phase modulation, right? But both are considered as a frequency variation in the carrier signal. Here the variation is the shifting in the high frequency and low frequency, right? Why it comes? Because here in the general equation, in the frequency modulation, in the general equation you can see you are integrating the message signal, right? So but while in the case of frequency modulation there is no need to do the integration. So there is a 90-degree phase shift in between the message signal here, right, without integration and directly. So you can see if you treat the message signal for the frequency modulation is in like this, but for the case of if you consider this is a empty, right? For the case of phase modulation you will have to take like this. This is a dy over dt empty. So you need to take the differentiation of this message signal here. So that's why there is a shifting in the high frequency and low frequency in the last two diagram. So here you can see, right, this is the theta 80 that already we have in this equation. Theta 80 2 pi 0 to t fit dt. So here I am considering the single tone modulation here. So 2 pi fct delta f by fm sin 2 pi fmt. So this term is known as frequency modulation, that is represented by beta here. So in the equation at last you will get theta 80, beta is delta f by fm, this is the frequency modulation index, and this finally we get the theta 80, this one 2 pi fct plus beta sin 2 pi fmt. So at last you will get the frequency modulated signal equations AC cos 2 pi fct beta sin 2 pi fmt. So there you have two cases for the beta here, right? If beta is very less than 1, then you will have the narrow band FM, and if beta is very greater than 1, then you will have the wideband frequency modulated signal. So there are the possibility to have narrow band FM and wideband FM depends on the value of beta here. So we will discuss the wideband FM, the wideband FM, that is wideband frequency modulator. It has the very wideband bandwidth. How it comes, we will learn here. So this is the general equation of frequency modulated signal. So for the wideband FM, this value beta should be very greater than 1. So what are we doing here? We can write these terms by using the Euler's theorem. Real value of exponential term of this angle, right? Real part means Euler's theorem, e to the power j theta is equal to cos theta plus eta sin theta. So this is a real part, so you can write real part of e to the power j theta. Similarly, we can write this equation real part of AC exponential of this angle j 2 pi fct plus j beta sine 2 pi fmt. Right, here I am writing this s bar t exponential of j 2 pi fct. I am splitting this equation in two terms. The first term is this term, the exponential of this term is known as we are representing with s bar t. So because this is a complex envelope, you can see this is a complex envelope, so we can say this is a periodic function of the time. So we can write s bar t is equal to s bar t plus k by ktm, where tm is the 1 by fm. Right, I hope this one is clear to all of you. So you can write this by using the periodicity of the signal. S bar t is equal to s bar t plus k by m. So this is the equation that we have, AC exponential j beta sine 2 pi fmt. Right, so here this is a, as we know, this is a complex envelope, that's why this is a periodic signal. So for the periodic signal we need to find the Fourier series to have the to find the bandwidth of the signal. So we have to take the Fourier series of this s bar t. So here I am right here, we are representing the exponential Fourier series equation that you all are aware about the all are aware about the exponential Fourier series equation. So this is a Fourier series coefficient. So here we have the Fourier series coefficient n is equal to for a one period of time fm minus 1 upon 2 fm 1 upon 2 fm s bar t exponential minus j 2 pi n fmt dt. If you take this integration, then you will get the equation like in this form, right, in this form. So this this equation is nothing but the Bessel function, this is a Bessel function. You can see j n beta, where the n is the order of the Bessel function. So j n beta equation, j n beta is the Bessel function. It is represented by this equation 1 upon 2 pi minus pi to exponential j beta sin x minus nx dx. So this equation is just similar like in this way. So we can say this Fourier coefficient is nothing but AC j n beta. So finally you can put this Fourier series coefficient value in this equation. S bar t you will get AC integration or summation of n is equal to minus infinity to infinity j n beta exponential j 2 pi n fmt. Now you have to keep this s bar t into this equation, right? So now you can see st is equal to s bar t exponential j 2 pi fct. So you have to put this equation into this. So you will get at last wideband modulated signal equation. This one is AC n is equal to minus infinity j n beta cos 2 pi fc plus nfm t. So you can observe here, these are the side bands. If you put n is equal to 0, then you will get the carrier frequency. If you put the n is equal to 1, the first sideband, second sideband, two sideband, third sideband, fourth sideband. So you will have infinite sideband in the case of wideband frequency modulation, right? You can see if you take the Fourier transform of it, you will get the infinite number of sidebands here. So practically, so ideally we can say the wideband FM has the infinite bandwidth, but practically it cannot be possible to have an infinite bandwidth of the system, right? These are the properties of the Bessel functions for the case of even order. So you will get j n beta is j minus n beta. J n beta, if you the sign is minus comes into the picture, then this property is for all to have the odd number of order of the Bessel function. These are the some properties. These are the main properties, and this is the special property of Bessel function. Here the summation n is equal to minus infinity to infinity jn square beta is equal to 1. So if I talk about the power of the wideband FM system, then you will have the power is, so power is AC square by 2 summation n is equal to infinity jn square beta, and this value this is the property of Bessel function would be equal to 1. So you will have the power is equal to AC square by 2. This power is equivalent to is nothing but the carrier power. So carrier signal power. So you can say for the wideband FM, the power is requirement is equal is same as the carrier signal power here. So practically, how can we decide the bandwidth of the system? So for this transmission bandwidth of frequency modulation wave, there is some rule to define the bandwidth is Carson rule. This is a Carson rule. So Carson rule specify the frequency modulated bandwidth, frequency modulated system bandwidth, right? So this is a so you can see bandwidth is equal to 2 times of FM plus delta F, you can write, or in other terms, if you take twice delta F, if you take FM outside to the equation, 1 plus delta F by FM, so 2 times of FM 1 plus beta. This is nothing but a modulation, frequency modulation index is represented by beta. So you can see it totally depends on the beta, right? For the narrow, this equation is valid for only wideband FM, but for narrowband FM, the bandwidth always equal to the 2 times of F max, that is equivalent to, this is nothing but the AM bandwidth, right? So narrowband FM is equivalent to the AM bandwidth, right? But for the wideband FM, you have to calculate the bandwidth with the help of this formula, like you can see here. Here you D here you can see D is representing the delta F by W is nothing but here FM, bandwidth of the modulated signal या फिर message signal, right? So this is the procedure to calculate the bandwidth of frequency modulated signal. So in this lecture we have covered the topic what is the analog modulation, amplitude modulation, frequency modulation, phase modulation, right? And then will this has covered the topic of narrowband frequency modulation, NBFM and wideband FM, and also the Carson rules to calculate the bandwidth of the frequency modulated signal. I hope this frequency modulation is clear to all of you. Thank you.